Hello everyone. I am Himanshu Mishra. I am a research scholar in the Department of Applied Mechanics, IIT Madras. And today I am going to discuss problems on heat exchangers as well as the free convection, problems on the free convection. And also I will revisit one problems from the previous week. Uh, Basically, last week I have solved problems related to the force internal heat transfer in the for the internal flows. So I will solve one problem that I could not able to finish last week. So in today's tutorial, I will be solving some basics question from the heat exchangers. So basically, we will look on this logarithmic uh, mean temperature of the heat exchangers, some basic questions like the classification of the heat exchangers, and we will be finding the Grashof number, Nusselt number in the free convection, in the problems of the free convection, and then we determine the heat transfer coefficient. This is similar to the last week that in the force heat transfer, force or the force convection, we identify the Nusselt number and then we found the heat transfer coefficient. In the free convection, you know that the Grashof number is which represent the ratio of the buoyancy force and the viscous force actually determine the free convection, and by using the correlation of Rayleigh number, Nusselt number, and the Grashof number, we will be finding the heat transfer coefficient and then the heat transfer rate. So let's begin with the first question. So the first question is belong to the heat exchangers. It says that the water at an average temperature of 107 degrees Celsius and average velocity of 3.5 meter per second flows through 5-meter long stainless steel tube in a boiler. The inner and outer diameter of the tube is given, which is 1 centimeter and 1.4 centimeter respectively. The heat transfer coefficient of the outer surface is 8400 watt per meter square degree Celsius, and we need to determine the overall heat transfer coefficient based on the given data. So we have given a steel tube basically. So these are my some outer parameters. And these are my internal parameters. And we need to determine the overall heat transfer coefficient, which is UI. So to determine that, we need to calculate the heat transfer coefficient or the internal heat transfer coefficient. And for that, we know that when there is a flow inside the tube, we can use the Nusselt number to find the heat transfer coefficient. So we already solved a plenty of problems in the last couple of weeks where we have looked some Nusselt number correlation for the laminar as well as in turbulent flow. So in order to determine whether the flow in the pipe is laminar or turbulent, again we know that we need to determine its Reynolds number. And once we get the Reynolds number, we can use that Reynolds number to first identify whether the flow is in laminar or turbulent. Second, we can use that Reynolds number in our Nusselt number correlation. And we will be using our Nusselt number based on the flow, nature of the flow, whether it is laminar or turbulent. So all these things we actually have done in the last week, week 6, week 7, for both external and internal flows. So I will be starting with the same thing today. So first we need to find the Reynolds number. So the properties of the flow can be you can easily get from books or the internet. So usually I don't write or give properties of the fluid like viscosity, density in the question because it is easily available. So we will be solving for the Reynolds number first. So the velocity is given as 3.5 meter per second, and the diameter, internal diameter, is 0.01 meter, which is 1 centimeter. The kinematic viscosity of the flow is 0.2 10 to the power minus 6 meters square per second. And on solving this, just calculating the Reynolds number, we will get a Reynolds number which is way larger than the critical Reynolds number. So for the pipe flow, we know that the critical Reynolds number is around 2400. So it is much larger than the critical Reynolds number. That means the flow is in turbulent. So the nature of the flow is turbulent. So now we have to use the Nusselt number correspond to the turbulent flows. I can get this Prandtl number based on the properties of the flow. It's just a ratio of the diffusivity. So one diffusivity we already have 0.2 10 to the power minus 6 here. And just we need to put the value of Reynolds number and the Prandtl number in the expression. So the Reynolds number we found is 130600 to the power 0.8, and Prandtl number is 1.58.4. So just on calculating, we will get the Nusselt number of 342. Now we need to find the heat transfer coefficient, which is basically the internal heat transfer coefficient. So 0.68 is my thermal conductivity K. And my heat transfer coefficient will be 23,324 watt per meter square degree Celsius. So now we got the heat transfer coefficient. Internal heat transfer coefficient, and in the question we already have given the heat transfer for the outer case. That means we have given the H naught, which is which is 8,400. So one thing that you need to take care is here I have used the thermal conductivity of the fluid. So in the Nusselt number expression, you need to use the thermal conductivity of the fluid, and in the question, the thermal conductivity of the steel tube is given. So you have to ignore this value. You need to use the thermal conductivity of the flow in the Nusselt number expression, whereas in the Biot number expression that we have solved some problem related to the unsteady flow, unsteady conduction in the past weeks. So to calculate the Biot number, you need to have the thermal conductivity of the solid in that expression. But here you need the thermal conductivity of the flow. So do not confuse about this aspect. So now we have the internal and outer heat transfer coefficient. And to find the overall heat transfer coefficient, we need to find the total resistance that is offered by the tube. So since we have a tube, so there will be flow outside the tube. So we know in the heat exchanger, particularly in the double type heat exchanger, there is a flow outside the tube and there is a flow inside the tube. And based on the direction, we usually classify whether it is in parallel heat exchanger or it is a counter heat exchanger. So anyway, we have a fluid inside this tube and outside this tube. So there will be heat transfer through convection inside this tube to the wall of the tube, and within wall there will be the heat transfer by conduction, and then there is a heat transfer from the outer wall to the outer fluid. So basically I can write my total resistance as so this is the resistance which is actually is present when there is a convection heat transfer between the internal tube and the internal wall. That means here in this region. And this is the resistance of the wall. That means when the heat transfer took place by conduction in the solid wall. So this is the resistance of that wall. And the third part is actually the resistance present when there is a heat transfer between the outer wall to the outer fluid. So here the heat transfer actually happened due to the convection, and we know that the heat transfer within the wall is actually happened due to the conduction. So we can write the resistance. Yes. So this expressions for the resistance we already actually considered in the past weeks when we were studying the conduction heat transfer. So at that time we actually found out the total resistance of the tube or the plane slab or the spherical body, and the resistance due to the convection heat transfer. Even in the first week, I guess, I have solved one problem in which I have identified the modes of heat transfer, basically due to the convection and conduction. And we know that the resistance will be different as well in all these different modes of heat transfer. So this is the resistance, internal resistance, and the resistance due to the wall. Since we have a pipe flow, so we are actually talking about the cylindrical walls. So the resistance for such wall will be given by this is my resistance, outer resistance, which is the outer flow is experiencing. So now we just need to put the value of HI, H naught, and other parameters like the diameter, thermal conductivity, and length. So this is the internal heat transfer coefficient that we found out using the Nusselt number. And my area would be, so basically I'm using here pi dl for the area. I'm using pi dl because we need to use the contact area of the flow and the wall. So if this is my pipe, there's a flow along the pipe. So we need to find this contact area along the flow, which which is pi dl. So here we can use the thermal conductivity of the pipe because we are actually investigating the resistance within the pipe, because there is a heat transfer due to the conduction within the pipe. So the K here is of a thermal conductivity of the steel pipe, whereas in the Nusselt number expression, we have considered the thermal conductivity of the fluid. Here I am considering the outer diameter. So we just need to calculate this. And the total resistance we will get by calculating the above quantities. So now it becomes easy for us to calculate the overall heat transfer coefficient. So my overall heat transfer coefficient will be given as 1 by total resistance and the internal area. And I have already used this internal area here. So this is my internal area. So now on calculating this quantity, we will get the overall heat transfer coefficient as 4055 watt per meter square degree Celsius. So in this question, we have given the heat exchanger and we have given the size of the heat exchanger, thermal conductivity of the pipe, and the outer heat transfer coefficient, and they ask us to determine the overall heat transfer coefficient. So to find the overall heat transfer coefficient, we need to use the resistance function. And since there is a flow inside the pipe and as well as outside the pipe, you can guess, even before solving, you can guess that you need to use the resistance inside for the inside heat transfer as well as for the outside heat transfer. So for the inside heat transfer, which is take place due to the convection, you again can guess that you need the inside heat transfer coefficient, which is not given in the question. So for that, you will you use the Nusselt number correlation that we have used for in the past week. So for choosing which correlation you have to use, you need to determine the nature of the flow, which can be laminar or turbulent. So we begin with determining the nature of the flow, and we found out it was turbulent flow based on the Reynolds number. And then we use the turbulent correlation for the Nusselt number, and then we form the internal heat transfer coefficient. Now, once we get the internal heat transfer coefficient, then you know that you can find out the internal resistance using the internal heat transfer coefficient. You can find the outer resistance as well using the outer given heat transfer coefficient in the question. And then you need to find the resistance between the wall, where the heat transfer actually takes place due to the conduction. So you already know this expression from the very beginning, and you just use that to find the total resistance. And once we get the total resistance, then we can easily find the overall heat transfer coefficient. So let's move to the second problem. So in the second problem, there is a double pipe parallel flow heat exchanger, and the heat capacity of the water is given. and the water is entering from 25 degrees Celsius and leaving at 60 degrees Celsius, and the mass flow rate is also given 0.2 kg per second. Again, there is a heating which is accomplished by the geothermal water, and we have given the properties of it as well as the inlet temperature, mass flow rate. The inner tube is thin wall has a diameter of 0.8 centimeter. If the overall heat transfer coefficient of the heat exchanger is 550, determine the length of the heat exchanger. So even before we solve this question, we know that we need to find the length of the heat exchanger. That means we should already know the heat transfer. Once we know the heat transfer using the Newton's law of cooling or the and the overall heat transfer relation of the Newton's law of cooling, we can find the area or the length of the desired system we have given. So for that, we record first the heat transfer rate. The rate of heat transfer given by since we have already given the properties and the temperature of the water, we can use this property to find the heat transfer. So this is for water. The mass flow rate is 0.2. Heat capacity we already have given in kilojoule. So the temperature difference is 60 minus 25. So we will get, on solving this, we will get the heat transfer 29.26 kilowatt. Now, as I already said, to determine the area or the length or the dimension of the heat exchanger, we need to use this relation. The heat transfer takes place, and the heat transfer is actually given by the overall heat transfer coefficient and the temperature mean logarithm. This is my logarithmic mean temperature difference. So to find out this log mean temperature difference, we need to find the outlet temperature of the geothermal water. So we have given the inlet temperature of the geothermal water, and we already given the inlet and outlet temperature of the normal water. So now our next task is to find the outlet temperature of the geothermal water. Once we found that, the next step is to find the log mean temperature. And once we find the log mean temperature, we need to find the length which comes from the area pi d l. So let's find the outlet temperature of the geothermal water in order to find this log mean temperature. So we already found the heat transfer based on the data and the temperature difference we are given for the normal water. So we will use this heat transfer. So this is for geothermal water. We already found out the heat transfer, and we need to find the outer temperature here. So my outer temperature will be so we already given the inlet temperature, we have already found the heat transfer, and we have given these properties also. So we just need to put the properties here. And on solving, on calculating this, the outlet temperature will be 117.4 degrees Celsius. So this is my outer temperature for the geothermal water. So now we have inlet and outer temperature for the geothermal water, and inlet and outlet temperature for the normal water. So we have these quantities now. So we can find now the log mean temperature difference. So in the question we have a parallel flow heat exchanger. So you need to take care while finding the delta T1 and delta T2, because for the parallel and for the counter case, these temperature differences will be different. So for the parallel flow case, my geothermal water and my normal water will be entered through the same direction. So based on this information, you can find my delta T1. My delta T1 is just a difference of inlet temperature of the geothermal water and the inlet temperature of the normal water. We already have all these quantities, and my delta T2 is the outlet temperature of the geothermal water and the normal water. So I just need to plug in this value and I will find delta T1 is 115 and delta T2 is 57.4. So my log mean temperature difference will be around 82.9 degrees Celsius. So now we found out the log mean temperature difference. So we can now found the area using this heat transfer relation. So we already found this log mean heat transfer relation. We already found the heat transfer. This is the first step we have done by solving this question. And we have given this overall heat transfer coefficient also. And there it is. And we need to find the length of the heat exchanger. So we found the heat transfer rate, which was 29.26. Yeah, this is 29.26 kilowatt. And diameter is 0.08 meters. The overall heat transfer is 550. So that will be 10 to the power 3. And my log mean temperature difference is 82.9. So on calculating, we will get the length of the heat exchanger is 25.5 meter. So let's solve another problem which is similar to this problem. So in this problem, we actually found out the length of the heat exchanger. Let's solve different question number 3 where we have to find the area of the heat exchanger. So in the question number 3, we have a double pipe counter flow heat exchanger to cool the ethylene glycol flowing at a rate of 3.5 kg per second, and we have given the temperature of inlet and outlet. Now it is to be cooled by water, and the water enters at 20 degrees Celsius and leaves at 55 degrees Celsius. So in this question, we have given the inlet and outlet temperature for both the fluid. So we don't need to find any temperature, just like we have done in the previous question. So the overall heat transfer coefficient based on the inner surface area is 250 watt per meter square degree Celsius. And we need to find the heat transfer, rate of heat transfer, mass flow of water, and the heat transfer surface area. So we can first find the heat transfer rate just based on the inlet and outlet temperature of the ethylene glycol. We can also find the heat transfer rate based on the inlet and outlet temperature of the water, but since we need to find the mass flow rate of water, we could not get the heat transfer because we have two unknown quantities, mass flow rate as well as the heat transfer. But we have already given the mass flow rate of the ethylene glycol, so we will be using the inlet and outlet temperature of the ethylene glycol. So what I am saying is, I can use this relation to find the heat transfer rate. Now I will be using for ethylene glycol. I shall use for the water as well, but since my m dot is not known, I cannot find Q. But for the ethylene glycol case, the m dot is given in the question. So we just need to plug all these values from the question. So mass flow rate is 3.5 kg per second. The heat capacity is 2.56 10 to the power 3 T minus 40. And my Q will be then 358.4 kilowatt. So this we have done for the previous question as well. We have found first heat transfer. We have found first the heat transfer using the normal water. And then we found the temperature of the outlet of the geothermal water, since we already know the heat transfer rate. So now instead of finding the temperature, since we have given the temperature, all the temperature we required, we need to find the mass flow rate of the water. So we can use the same relation but for the water case. I'm using the same relation, but now for the water case. So the heat transfer rate will be same for both the cases. So again, I will repeat. So in earlier question, we found out the T out. We already found the Q here. And then we found the T out. But now, since we have given the T out and T in, we need to find the M here, M dot here. Since M dot is the unknown quantity here. So it will be the water, my m dot becomes this. We have already found Q, which is 358.4 watt, and my heat capacity of the water is 4.18 10 to the power 3. And this is my given temperature difference from the question. And And on calculating this, we will get mass flow rate is 2.45 kg per second. So we found first the heat transfer, and in the second part we have found the mass flow rate. Now we need to find the area of the heat exchanger. So likewise we have done in the previous question, we will be using the relation, and we first need to account the log mean temperature difference, and then we will find the area of the heat transfer, heat exchanger. Now in this question we have the counter heat exchanger, unlike in the previous question where we have the parallel heat exchanger. So the value of delta T1 and delta T2 will be different now. So my delta T1 now is this for the ethylene glycol, and this is for my water. This is the outlet temperature of the ethylene glycol, and this is my inlet temperature of the water. So now the delta T1 is the inlet temperature of the ethylene glycol and the outlet temperature of the water, and delta T2 is outlet temperature of the ethylene glycol and the inlet temperature of the water. For the parallel heat exchanger, we had the inlet temperature, both inlet temperature at the delta T1 and both outlet temperature at the delta T2. So just putting these temperature values from the question, we will get delta T1 as 25 degrees Celsius and delta T2 is 20 degrees Celsius. So my log mean temperature difference is which will be around 22.4 degrees Celsius. Now I can directly find the area of the heat exchanger. So this will be, we already found the heat transfer at the first part of the question, 358.4. We have given the overall heat transfer coefficient, and we found the log mean temperature difference. So on solving this, on calculating this, my area will be 64 meters square. So in the both question number 2 and in question number 3, we found first the heat transfer rate based on the inlet and outlet temperature of any of the fluid. And we have given the inlet and outlet temperature of the normal water in the previous case. So we use that expression. Here in this question, we use the inlet and outlet temperature of the ethylene glycol because we have given all the properties of the ethylene glycol. But for the water case, we have not given this mass flow rate. So we found the heat transfer rate. Then using the same relation for the water, we found the mass flow rate. So sorry, earlier we found the heat transfer using the relation for the ethylene glycol, and we use the same relation for the water to find the mass flow rate of the water. And then we use, since we need to find the area here, we need log mean temperature difference, and it is given in the question that it is a counter heat exchanger. We need to first check whether it is parallel or counter, and based on that we found the log mean temperature difference, and then we can find either length or the area. So let's move to the question 4. So this is a question which I cannot able to solve last week, and I will. So basically, this question is related to the internal flows, force convection. In this question, this ethylene glycol flows at 0.01 kg per second through a 3 mm diameter. The tube is coiled and submerged in the well-stirred water maintained at 25 degrees Celsius. If the fluid enters the tube at 85 degrees Celsius, what heat rate and tube length are required for the fluid to leave at 35 degrees Celsius? Neglect the heat transfer enhancement associated with the cooling. So we need to find the tube length that is required to attain the outlet temperature for the fluid 35 degrees Celsius. So for this we need to find first the convection heat transfer rate, and then we will be finding the length and area. So my convection heat transfer rate will be I have given the mass flow rate. The heat capacity is 2562. This is my temperature difference. So my heat transfer is 1281 watt. Now for the constant surface temperature, the heat transfer will be so area would be given as. Now we need to find the mean temperature difference. We already given the mean temperature difference here. We need to find the heat transfer coefficient because we have not given any heat transfer coefficient in the question. So for the heat transfer coefficient, we will be using the Nusselt number relation. And first we need to check whether the flow is in laminar or in turbulent condition. And accordingly, we will be using the Nusselt number correlation. So my Reynolds number will be, since we have given the mass flow rate, I am writing my Reynolds number expression in terms of mass flow rate. So 0.01 is my mass flow rate. 0.003 meter is my diameter, and my viscosity, dynamic viscosity is 0.52 10 to the power minus 2 Newton second per meter square, and my Reynolds number is 813. Now, based on the Reynolds number we get, our flow is in laminar state, so we can directly use the Nusselt number as 3.66. So my heat transfer coefficient will be 3.66 K by D. So here, as I said, we will be using the thermal conductivity of the fluid. My thermal conductivity of fluid is 0.26, diameter is 0.003, and this is my heat transfer coefficient. So now I can find my area based on this expression. So we need to just plug in the values and we will find the area is 0.1448 meters square. So the question is similar to the previous, even though it is based on the internal force convection. We found the heat transfer first, and we found the heat transfer coefficient based on the Nusselt number correlation. We found the flow is laminar, so we use a laminar Nusselt number correlation to find the heat transfer coefficient. And from the heat transfer equation, Newton's law of heat transfer expression, we just find the area. So now let's move to the question number 5. So this is a statement question. We need to answer the to this statement which are given as A and B. So the first statement is, consider a hot-boiled egg in a spacecraft that is filled with air at atmospheric pressure and temperature at all times. Will the egg cool faster or slower when the spacecraft is in space instead of on ground? So the question says that we have the hot-boiled egg in the spacecraft. Now we need to find whether the egg cool faster when the spacecraft is in the ground, or whether the spacecraft is in the space. So we have two cases here. So first, my spacecraft is in the ground. This is my case A. And in the case B, my spacecraft in the space. And inside the spacecraft, of course, there is a air filled inside the spacecraft. So now we need to determine the egg contained in this spacecraft. So in which case the egg will be cooled much faster, in case A or in case B. So here the correct answer is in case A. So in case A, the egg will cool much faster. So assuming the cooling is actually happens due to the free convection. So we know that the free convection, the gravity is important. That means there is a buoyancy which is responsible for the free convection heat transfer. So this is my egg, and my egg is in high temperature Ts, and this is my temperature at far from the egg, the temperature of air. Now close to the egg, we know that the air is much warmer, and this warm air is actually moved upside. It actually flows to the upside due to the buoyancy. Since the density of the warm air gets changed, decreases, and therefore due to the buoyancy, the warm air will move upward or flow upward, and the region is replaced by the cool air. And my warm air will flow upward, and this region will replaced by the cool air, and this cool air will become warm, and this process will continue. And this is what the free convection heat transfer is. So this free convection heat transfer occurs due to the buoyancy, and the gravity plays a very important role in this buoyancy term. And we know that in space, the effect of gravity will be much weaker. That means the heat transfer due to the free convection will be much weaker than on the ground. And therefore, in the ground, the free convection heat transfer will be much more dominant due to the gravity. And therefore, the correct answer for this question is in ground, the heat transfer will be much efficient, and egg will become cooler much early compared to the in space. So the statement B says that in which mode of heat transfer is the convection heat transfer coefficient usually higher, natural convection or forced convection? So we already now discussed the mechanism of the free convection in a very brief manner. So this mechanism involves the flow of this warm air towards the upside, which eventually replaced by the cool air. The flow of this air actually determines the heat transfer coefficient rate. Whereas So there is some heat transfer coefficient rate. Here, let's say this is H1 for the free convection. And now consider a case of the forced convection. So in the forced convection, we actually so let's say this is my fan. So this is the example of the forced heat convection. So when we switch off the fan, we actually make the flow happen, and this flow is the velocity of this flow is much larger than the air in the previous case or in the free convection case. So in the free convection case, the velocity is v1, and here, due to the fan is rotating, my velocity of the air is v2, and we know that this v2 is much larger than v1. And due to this, my heat transfer coefficient in force case will be much higher than in the free case, and therefore the heat transfer will be much faster in the forced convection when compared to the free convection. So let's move to the question number 6. So until now we have actually discussed the problems related to the heat exchangers. Now we will discuss the problem related to the free convection. So in this question, there is a 10-meter long section and a 6 centimeter diameter horizontal tube. Water passes through a large room whose temperature is 22 degrees Celsius. If the temperature and the emissivity of the outer surface of the pipe are 65 degrees Celsius and 0.8, determine the heat rate of the loss by natural convection and the radiation. So I okay, let me finish the question first and then to decide. So here we have a tube. The temperature of the air is 22 degrees Celsius and the temperature of the tube surface is 65 degrees Celsius, and we have given the diameter and the length of the tube. And we need to determine the heat transfer by natural convection and the radiation. So to determine the heat transfer, we will be using the Newton's law of heat transfer because the heat transfer is due to the convection, free convection basically. And we have given the temperature difference, we have given the area, but we have not given the heat transfer coefficient. So first we need to find the heat transfer coefficient, and then we will find the heat rate. So here in this case, we will be finding the heat transfer coefficient considering the fact that the heat transfer is due to the free convection or the natural convection. So the Nusselt number can be given as for such cases. This is my Nusselt number correlation, so you don't need to memorize this lengthy expression actually. So here we have the Rayleigh number and the Prandtl number, which are again unknown. So Rayleigh number is unknown. We know the Prandtl number, which is just based on the properties of the flow. And the Rayleigh number is given as so this quantity is my Grashof number. So the Rayleigh number is actually given as the Grashof number and the product of Grashof number and the Prandtl number. And my volume coefficient beta can be given as This TF is my mean temperature. So TF is my TS. So we have already given this temperature. So my TF will be 43.5 and then beta would be. So to find the beta, we need to convert this temperature into Kelvin. So always convert the temperature into the Kelvin to find the beta. And my beta will be 316 Kelvin inverse. So my Rayleigh number will be, this is my gravity acceleration, this is my beta, and my temperature difference is already given in the question, and the diameter is also given. The kinematic viscosity is 1.7 10 to the power minus 5, and my Prandtl number for the gas is 0.72. So on calculating this, the Rayleigh number would be 692,805. So we know the Rayleigh number, we know the Prandtl number as well. We just need to put the Rayleigh number and the Prandtl number in this Nusselt number correlation. And when we do this, we will get the Nusselt number as 13.15. And we can find the heat transfer coefficient based on my Nusselt number, which is 13.15. And my thermal conductivity of the fluid is 0.26 and the diameter is 0.06. So my heat transfer coefficient will be 5.893 watt per meter square degree Celsius. So now we will use the Newton's law of cooling. We found the heat transfer coefficient. We need to find the area we need to find the heat loss. We already given the area. Since we already given the diameter and the length, we know the area. We found out the heat transfer coefficient and we know the temperature difference. So it is just, we need to substitute these values. This is my heat transfer coefficient. And my area would be pi dl. And the temperature difference will be, so just putting the value of diameter and then we will get the heat transfer as 0.776 watt. So this will be my heat transfer rate. So in this question we need to find the heat transfer rate. We have given the dimension of the tube and the question says that the heat transfer tube is actually accomplished by the free convection or the natural convection. So for that we first find the heat transfer coefficient. We use the Nusselt number correlation. And in the Nusselt number correlation, which is a function of Rayleigh number as well as the Prandtl number, we found the Rayleigh number. So once we get the Rayleigh number, we found the Nusselt number, and from the Nusselt number we can easily find the heat transfer coefficient rate, which is H. And then we found the heat transfer rate. So let's move to the question number 7 quickly. And question 8 probably I will solve in the next class. So in the question number 7, the plant and manufactured can retain the cans at temperature tested in water bath before they are shipped to ensure that they will withstand temperature of 255 degrees Celsius during the transportation. The cans moving on a conveyor enters the open hot water bath, which is 0.5 meter deep, 1 meter wide, and 3.5 meter long, and moves slowly in the hot water towards the end. Some of the cans fail the test and explode in the water bath. The water contained is made of sheet metal and the entire container is about the same temperature as the hot water. The emissivity is given. The temperature of the surrounding surface is 20 degrees Celsius. And we need to find the heat transfer. So So we need to find the total heat transfer. So we are assuming that the heat transfer is actually takes place here due to the convection as well as the radiation here, because we have given the emissivity. So I will skip the radiation part because we have not covered the radiation. So you may not have the idea about the radiation heat transfer now for now. So we will be solving the heat transfer rate due to the convection. So there are the cans, and these are inside the water bath, which is at 55 degrees Celsius, and they are moving. So the cans have a surface temperature, and there will be the heat transfer between the cans and the water bath. And some of the cans explode also. So let's say this is my water bath at temperature 55 degrees Celsius, and these are my cans arranged in a series. Now to find the heat transfer rate, the question is actually similar to the previous question. So we will be using the Newton's expression for the heat transfer rate. The temperature of the surrounding air and surfaces is 20 degrees Celsius. So to find the heat transfer rate, we need to find the heat transfer coefficient. So again, assuming that the heat transfer is due to the free convection, we will be using the same Nusselt number relation that we have used in the previous question. So we will be using this Nusselt number correlation. So we will be using this Nusselt number relation, but to use this Nusselt number correlation, we need to find the Rayleigh number. And we know that now that Rayleigh number is the product of Grashof number and the Prandtl number. This is my Grashof number. So just putting the values from the question. So again, we need to find out this beta also. So for beta is given as the inverse of the mean temperature, and the mean temperature is the average of the temperatures we have given, which is 37.5 degrees Celsius. Now, as I have said, to find the beta, we need to convert this mean temperature into the Kelvin. So it is given in degrees Celsius. So I will add from 273. So my beta will be 0.00322 Kelvin inverse. So now I can use my Rayleigh, this beta, to find the Rayleigh number. So we got beta is 0.00322, and my temperature difference is 55 minus 20. The length is given as 0.52. And my kinematic viscosity is 0.67 10 to the power minus 5 square. And the Prandtl number is 0.72. So just calculating the Rayleigh number. So you can calculate the Rayleigh number is 3.56 10 to the power 8. Now you can use this value of Rayleigh number here to find the Nusselt number. So the Nusselt number is 89.84, and you can find the heat transfer coefficient. You know that the heat transfer coefficient is and the Nusselt number relation is given by this. So the heat transfer coefficient will be Nusselt number multiplied by thermal conductivity of fluid divided by the diameter of the cans. So the thermal conductivity of fluid is 0.026. Nusselt number is 89.84. So this is my heat transfer coefficient. And now we will be using the Newton's law of cooling. We found the heat transfer coefficient. We already given these properties. 4.75 multiplied by so for the area, we have given the dimension of the bath, water bath. Which is okay, so we have given the 0.5D, 1 meter wide and 3.5 meter long. So this is 0.5, 3.5 meter, and this is 1. So there will be the convection here and here. So my area would be 0.5 multiply 1 plus 0.5 multiplied by 3.5, and the temperature difference we have given is 55 meter 20. So on solving, my heat transfer will be 748.1. Since we have given the emissivity, we can find, so this is my heat transfer due to the free or the natural convection. We have given the emissivity. So we can find the heat transfer due to the radiation here. So again, for the radiation heat transfer, we need to use this temperature in the Kelvin, not in the degree Celsius. So we have given the emissivity, and we have given the area here. So this is my area, and this is the constant, Stefan Boltzmann constant. My area. My Stefan Boltzmann constant is 5.67 10 to the power minus 8. And I convert my temperature into the Kelvin. So my radiation would be 750.9 watt. So the total heat transfer would be heat transfer due to the convection and heat transfer due to the radiation, which is 1499 watt. So in this question we found the heat transfer due to the convection, and the procedure is similar to the previous question. We found to find the heat transfer coefficient we need a Nusselt number, and to find the Nusselt number we need Rayleigh number. So first we found the Rayleigh number, then Nusselt number, and from the Nusselt number we got the heat transfer coefficient, and then we found the from the heat transfer coefficient by using the Newton's law we can easily get the heat transfer due to the free convection. Now we have also given the emissivity, so we found the heat transfer due to radiation as well, and then we find the total heat transfer, which is the summation of the heat transfer due to radiation and the free convection. So the last question we will solve in the next week. So in this week we have actually covered the question related to the heat exchangers, the free convection, as well as the one question from the forced convection. The only main difference between the forced and the free convection is the use of the Nusselt number and the use of the Nusselt number correlation actually. The common thing is to find the heat transfer coefficient in both the cases. So based on the Nusselt number correlation, you will be decide whether where the problem you are solving is free convection or the forced convection. But the motivation is same. From the Nusselt number, you will be finding the heat transfer coefficient and then the heat transfer rate. We have solved some basic question from the heat exchangers, where we found the area or the length of the heat exchanger. So for that we need the overall heat transfer coefficient. We need a heat transfer. So first we found the heat transfer, and then we also need the log mean temperature difference. For the log mean temperature difference, we need both inlet heat temperature and both outlet temperature of the fluid. Since we have a two fluid, we have two outlet temperature and we have two inlet temperature. So we need all these temperatures. So we have looked a couple of questions related to this, where we are finding the outlet temperature or the mass flow rate, heat transfer, and then the log mean temperature to find the area geometry specification of the heat exchangers. So you can look this video on the YouTube. I will upload this video on the YouTube, and you can find this PDF from the link. So you can revise this lecture through the video or in the PDF. Next week, I will be solving some more questions related to the heat exchangers, basically problems involving some different concepts, but the motivation will be the same, finding the heat transfer or the area or the geometric parameters of the heat exchangers. And I will again revisit one of the questions which I have left here, the last question, which is based on the free convection heat transfer. I guess it is related to the heat exchanger. So yeah, we will look some more problems on the heat exchanger. Thank you.